All right, sir.
Okay, so Assalamualaikum. This is your Thermodynamics 2 class, and today is lecture number 27. So, can anyone confirm what's appearing on the screen right now?
Sir, lecture number 27, roto dynamic machinery.
Okay, thank you so much. Okay, so as it is mentioned that now we are going to the next topic, which is the rotodynamic machinery, so compressible flow lecture. The course is till that point where we have stopped in the last lecture. Okay, so now we will discuss briefly for this rotodynamic machinery. I think it will just take 2 lectures, and from the next class we will finish this, and after this 2 classes we will discuss the paper and the pattern of the paper. Okay, so here this chapter is not linked with your chapter that is from your book. Okay, so this I will just extract some of the data from the reference books. So you just have to look into slides, okay, so that you will understand. So first thing is that what is the rotodynamic machine or machineries? Basically, that in your gas turbines or steam turbines, we have many times discussed that there is a steam power plants and gas power plant. We have many times discussed the turbine. So the turbine portion is basically the rotodynamic machine. Okay, so that is it is mentioned from the word as also rotodynamics. So it's mean there was some rotary machine, and we are just going to analyze some dynamics of that rotary machine. So in case of turbines, we have the rotary motion, then we send it to the generator. Okay, so we will discuss about it, and this is the just a definition of dynamic machine in which fluid flow freely through an impeller or a rotor. So here there is a picture of the gas power plant. So if you can see over there is turbine. Okay, so this turbine is basically the rotodynamic machine, and whatever the rotary motion that is generated due to the impact of the steam. Okay, so and it will send it to the generator section. Okay, so this portion is basically rotodynamic machine. Okay, so as we are now discussing on only the steam machine, however, there are some other rotodynamic machine as well. For example, the same turbines are used for the that is for the water purpose as well. So these are called a water turbine. So here we are only discussing steam turbine. However, the principle are almost same. Okay, so there is not much difference in the principles. Okay, so we will just look for the definition. The transfer of energy between the fluid and the rotor is continuous, and the change of angular momentum of the fluid cause or as in the result of torque on the rotor. Okay, so an important point over there is that steam turbine is a prime mover in which work is obtained by gradual change in momentum of steam. Okay, so what is the meaning of prime mover? Okay, so we will just take a small example for this. For example, in our daily household appliances, we use fans. Okay, so in the case of fan, the fan is basically rotating with the help of some motor. Okay, so in the case of fan, the motor is the prime mover. So any source that is providing rotation or motion to any other machinery, so that is called a prime mover. So another example, a small example is the pump that is we use to throw water from lower height to upper height. So in the case of pump also, there is a motor that is running the pump. So the motor is the prime mover. And in the case of turbine, that is the steam turbine. So steam turbine is prime mover because steam turbine is responsible for running the generator. Okay, so that's why the steam turbine is prime mover in case of your gas power plants or steam power plants. Okay, so the basic principle that from Newton's second law, we also already know that the rate of change of momentum is equal to net force. Same principle applies for the steam turbines. Okay, as we already know that in steam turbine there are different set of blades. Okay, and if you remember, I already show you one video that is related to gas power plant, and there are many blades. That is a set of stationary blades and then moving blades. Okay, and due to the motion of these blades, the rotation will be produced inside your turbine, and then that the blades are connected to one single shaft, and due to the rotation of that shaft, the generator will move. Okay, so in the case for the blade, we just take a small example. So first example we just take for the wall. Okay, so a stationary wall, and there is a nozzle, and some fluid is coming out of it with some velocity that is v1, and v2 is equal to 0 because it's a stationary wall, so we can say that this v2 is equal to 0. So in this case, if we can notice over there the impulse force. So impulse force basically m into change in velocity. So in this case, for the stationary wall, we have m into v1. However, if we just take the example for the blade, so for example, this is the blade, a curved blade. Okay, so basically, in your turbine, the blade geometry is look like this. Okay, so this is the representation of blade. So in this case, for example, a same nozzle, there is some fluid that is coming out of it. So either it is the steam or either it is the water. Okay, so if in the case of water turbine, we have the water. In case of steam turbine, we have the steam at this point. So with the velocity v1, and if we can assume there is no friction over there, okay, on the, we can say the curved section, okay, this, and in the blades we call as an inlet, and this is the outlet. So the same velocity, but with the opposite sign, is at the outlet. Okay, so in this case, your impulse force become m into change in velocity. So this will be equal to 2m v1. Okay, so in this case, your impulse force is more as comparison with the stationary one. So this impulse force is basically responsible for moving of your blade. Okay, so that's why your blade is more like a spherical, or you can say curved shape. So, but that will be also different in each type of turbine. So it is not like this that all the turbines have the similar type of geometry. So all the turbines have different sort of geometries. Okay. So this is the just overview of the impulse force that is used in the blades. So this is just a theory. So you just have to go through it. That a steam turbine is a device that extracts thermal energy from pressurized steam and uses it to mechanical work on a rotating output shaft. So working principle, so the generation of high velocity steam jet by the expansion of high pressure steam, and then conversion of kinetic energy so obtained into mechanical work on rotor blades. And steam turbine consists of essentially two parts. So one fixed nozzle and moving curved blades. A high velocity jet coming out of steam nozzle impinges on the curved blades. Blades are so curved that steam enters without any shock. Steam glides tangentially on the curved blade, fixed to the periphery of the moving wheel. Blades start to move due to the change in direction of flowing steam. Steam turbines, and they convert high pressure steam into high velocity jet to the steam nozzle, and convert high kinetic energy of steam into mechanical work by changing direction of steam. And steam turbines are used for in power plants to drive electrical generator, to propel large ships, submarines, drive fans, compressor pumps. Okay, this is just a theory. You just have to go through it if you want some useful information. So this is how your steam turbine looks like. I hope you already have the idea that in our steam turbines we have the high pressure turbine, we have intermediate pressure turbine, we have low pressure turbine. So collectively, all these turbines are connected to the same shaft, so that because in each section we have different pressures. So our main target is to develop such type of arrangement so that our rotation will be consistent. Because, for example, if your high pressure turbine is rotating with some other speed and intermediate pressure turbine is rotating with some other speed, okay, so then it is not good for your generator as well, because otherwise you will not produce a consistent electricity from the generator. Okay, so that's why the arrangement is like this, that all the turbines are connected in a pattern, that the velocity of all the high pressure, intermediate pressure, and low pressure turbine are same. Okay, so now coming towards the classification. So based on classification, our impulse, the turbines that is classified as a mode of action. So we have two turbines, we have impulse and reaction turbine. Then according to direction of steam flow, we have axial flow turbine, radial flow turbine, and then according to exhaust condition of steam, we have condensing turbine, non-condensing turbine, and then we have the low pressure, medium pressure, and high pressure turbine. And according to number of stages, we have single stage and multi-stage turbine. So I hope you already know stage. Okay, stage mean that number of, for example, if you have set of blades, so this is just a blade, and then you have one set of blade which is the moving blade. Okay, so we have stationary blade and moving blade. So collectively, this whole set is called a stage. So in most of the turbine, we have different set of the moving blade and stationary blade. So collectively, these are called multi-stage turbines. So this is just an overview. In this lecture, we will just talk about impulse and reaction turbine because this is just a main classification of the turbine. And because we are not going into much detail, we just see overlook it that how you can analyze the turbine and how to do some calculations regarding the efficiency of your blade and stage efficiency. So we just start looking briefly. So coming towards the impulse turbine first. Okay, so before starting this, we will look for one video, okay, so that you will get some idea that what is the impulse turbine and reaction turbine, and after this we will continue from this point. Okay, so here is example of impulse turbine, and this is the reaction turbine. So first we will see the impulse turbine. Okay, so in the impulse turbine, we have the blades. Okay, so these blades are basically moving blades, and it is connected to one wheel. You can say wheel or runner, and then it is connected to the shaft. Okay, so these all set of blades are basically the moving blades, and this is the fixed nozzle from where your steam is injected, and that steam impinges on the blade geometry, and due to the impulse force, okay, so that is generated on this side, these blades will rotate. So this is just a basic principle. So now we will look for the video. Okay, and due to this motion, our turbine blades move and in result with the rotatory motion. Okay, so now coming towards the next. Okay, so and this turbine is connected to the generator section. Okay, and as a result of this rotation, our generator we can generate some electricity from the generator section. Okay, so now looking towards the principle of reaction turbine. Okay, so this is your reaction turbine, and in reaction turbine, the only main difference is that we have the nozzles. Okay, but this nozzle is movable nozzle. Okay, and it is connected to the shaft. Okay, so if you can notice over there, and then we have set of stationary blade, and then we have moving blades. Okay, and also if you can notice over there, there is a fixed nozzle as well. Okay, in the same case as the impulse turbine. But where is the fixed nozzle? We didn't see it. Basically, all the stationary blades that is over there, which is in the blue color, these all stationary blades act as a nozzle. Okay, when the steam passes through these stationary blades, so at the end of this section, we have the nozzle effect, the same effect that is in the nozzle. That's why we call as just a fixed nozzle to all these stationary blades. Okay, and collectively, this one portion is called stage. This is another stage. This is another stage. Okay, so this is just a basic difference for your reaction turbine and impulse turbine. So now we will go back and look for this theory that so that you will get some understanding. So impulse turbine basically work on Newton second law of motion, that is change in momentum produces force. In this turbine, steam coming out of boiler expand in stationary nozzle and its kinetic energy increases. This steam then impinges on the curved blades mounted on a periphery of the rotor, that is the rotating wheel. As the steam glides tangentially over the blade, its direction is changed, changing its momentum. So here is the steam is coming in and it is coming out by using, if we can say that this is the frictionless, or if there is a friction, then we have to include the friction effect as well. And due to the impulse force that is generated at this side, the blades start rotating. And we called this portion as inlet and this portion as outlet. Okay, so in impulse turbine, the total expansion takes place in steam nozzles only. Okay, so as you already know, that nozzle are basically expansion devices, so the pressure decreases at the in the nozzle. So hence pressure remain also constant while moving through the blades. So this is the important point, that your pressure only changes in the nozzle in the case of impulse turbine. However, in case of your pressure remain constant while moving through the blades, and blades are the moving blades. Velocity of steam rises in the nozzle and fall while passing through turbine tube. So we will see one figure. So this is the example of your impulse turbine. So a jet of steam is impinges on the rotor, or you can say blade. Okay, and due to this effect, the rotor moves. If we can just take a cross section of these. So for example, we can say that these all are the fixed nozzle. Okay, so that is, and this is the moving blade. So our steam is coming in from this, and this is your end of the nozzle. Okay, and if you can notice over there, your impulse turbine blades are mostly a cup shape. Okay, so it is just like this, and due to this geometry also, the pressure also remains same when it is moving through these sections. Okay, so we will see the pressure and steam or velocity graph for impulse turbine. So if you can notice over there, there is a steam pressure line and there is a steam velocity line. So for example, if we can say that this is the portion. Okay, so this area is basically the nozzle, and this is the moving blade. Okay, because if you can notice from the figure, so you will easily find out that this is the moving blade and this is your nozzle. So if we can take the pressure only, so for pressure, so at the end of the nozzle, the pressure decreases. Okay, so pressure will almost reaches to the this limit, and when the steam is passing through the moving blades, the pressure remain constant. Okay, so it will be constant when the steam is coming towards the moving blade section. And if we can take a look for the steam velocity, so the steam velocity is maximum at the outlet of the nozzle. Okay, and then it start decreasing, because definitely when it hits the blade, the steam, it absorbs some kinetic energy and the velocity decreases at this portion. And due to this effect, the velocity decreases in the moving blade section. Okay, so this is just a general graph for the pressure and velocity for impulse turbine. So I hope you get some understanding. If you have any question, you can also ask me. Okay, so now if we just take a look for the moving blade graph only, because in the previous picture we are just considering the nozzle graph and also moving blade. So if we just take a look for that, this is the moving blade and connected to the shaft. So in the case of impulse turbine, our pressure is constant when it is passing the moving blade, and the velocity decreases. Okay, so this is just a graph for the moving blade section. Okay, and then coming towards the reaction turbine, so first we will see an example, that is a steam device. So that is shown over there. So this is basically the same principle on which your reaction turbine will work. So in this case, there's, if you can see, there is a sphere. Okay, so and there is some burning of coal, and then due to this effect, we are going to generate steam inside this sphere. And when the steam is generated inside this sphere, so, and there are, if you can notice over there, there is two nozzle that is connected on the two opposite side. Okay, and by using the action and reaction forces, that is the Newton third law. So if the steam is generated, so this sphere start rotating around this, and the same principle applies to reaction turbine. Okay, so reaction turbine work on principle of Newton third law of motion, that is reaction force developed is equal and opposite to action force. In this turbine, the rotation is caused by reaction force generated by momentum change of fluid. First reaction turbine, which is shown over there, which looks like this, and it consists of radial tube which are connected to a supply tube and are free to rotate about a vertical axis. The end of each radial tube is designed as a nozzle causing acceleration of fluid through radial tubes. The rate of increase in momentum of steam along flow in radial tube is provided by force on the steam flow from the nozzle wall in the direction of steam flow. An equal and opposite force act on the nozzle wall, causing the tube to spin around in the direction opposite to the steam. So the same example which we already discussed in the previous slide. Okay, so which is just a principle for the reaction turbine. So now coming towards the reaction turbine, same velocity and pressure diagram. So in this case, if you can notice in the previous figure, we already discussed that in the reaction turbine we have set of stationary blade and moving blade. So all your stationary blade act as a nozzle in the case of reaction turbine. Okay, so in this case, the pressure drop occur both in stationary blade and in rotor blade. Enthalpy drop change into kinetic energy in both blade. So why there is a pressure drop now in the moving blade as well? So if you can notice over there, in the case of impulse turbine, the blades are like this, which is a symmetrical blades. Okay, in the case of your reaction turbine, it is unsymmetrical. Okay, you can notice over there, it is more type of aerofoil shape. Okay, so due to this geometrical configuration, the pressure also drop when the steam is passing through this moving blade section. So if we can just take a look for the pressure and velocity diagram, that is the graph. So the same thing. So until this region, we have the, you can say, stationary blade or nozzle, or here we have the moving blade. So at the end of the stationary blade or the nozzle, the pressure decreases. Okay, and then as the steam passing through the moving blade section, it further decreases. Okay, so in the case of impulse turbine, it is constant pressure. In the case of reaction turbine, it's further decrease the pressure. Then if you can look for the velocity, so at the end of the stationary blade, the velocity is maximum. Then as it's moving towards the moving blade section, the velocity decrease because there is an absorption of the kinetic energy. So that's why your velocity decrease in the section of the moving blade. Okay, so this is the pressure and velocity graph for the reaction turbine. Now similarly, if we can just so this is just the same thing which I already told you, that in the case of impulse turbine, the blades are more of the cup shape, and in the case of reaction turbine, it is unsymmetrical type, and it is more type of aerofoil type shape. So that's why there is a decrease in pressure. So rest of this is just a theory, so you just have to go through it. I have already told you that unlike impulse turbine, no nozzle as such are mounted in the reaction turbine. Actually, the steam is directed into the moving blade by a fixed blade designed to accelerate the steam as the blades are unsymmetrical. That is the nozzle shape. So in the case of impulse turbine, reaction turbine, all the stationary blades act as a nozzle. The result is an increase in velocity over that of the moving blade in case of reaction turbine, and these blades form a wall of moving nozzle that further accelerate the steam, and the steam acceleration in the moving blades result in the reaction on the blades. This is just a theory and you have to go through it. So if we can take a look for the moving blade section, pressure and velocity. So the pressure also decreases in the moving blade section and velocity also decreases. So in this case, both pressure and velocity decreases in the moving blade section. However, in the case of impulse turbine, the pressure constant remain constant and velocity only decreases. So this is just a difference. And for example, if I give the same graph that you have to draw the pressure velocity diagram for the moving blade section. of impulse turbine and reaction turbine in the paper or your exam. So you have to draw the simple graph of pressure and velocity. Okay, so this is just same graph. Now we are considering more number of blades. So first example over there is the impulse turbine and this is the reaction turbine. So in the case of impulse turbine, for example, if we can just consider that there is a fixed blade, then there is a moving blade, and moving blades are the curved shape, and these fixed blades basically represent the nozzles. Okay? So fixed blade, moving blade, fixed blade, moving blade. Again, in the reaction turbine, we have fixed blade, moving blade, or of aerofoil shape or unsymmetrical shape, fixed blade and moving blade, fixed blade then moving blade. Okay, so now if we can take a look for the pressure velocity diagram, or in this type of multiple, you can say multi-stage turbine. So in this type, the pressure decreases at the end of your stationary blade, then remain constant, then decreases, then remain constant, then decreases, and then remain constant. That is for the case of impulse turbine. Velocity at the end of stationary blade maximum, then decreases. When it passes through the moving blade, it further increases. When it passes through the fixed blade, again decreases. Then moving blade, so same pattern will be followed. So in case of reaction turbine, at the end of fixed blade, the pressure decreases. When it's sent to the moving blade section, again it decreases, further decreases when sent to the fixed blade section, and further decrease until it reaches to the end stage. So it is continuously decreasing. Then the absolute velocity at the end of your fixed blade section, it increases, then decreases when it's moving and sent to the moving blade section, further increase, then decrease, then increase, and then decrease. Okay, so if we can look for this graph, and there is another difference. So one more difference over there is that if you can look for the velocity. So in the case of your impulse turbine, the velocity, absolute velocity of steam is more as comparison to the reaction turbine. Okay, so that is the basically case that your impulse turbine is generating more power as comparison to reaction turbine if there is a similar type of configuration, because the velocity of steam is more in the impulse turbine. So that comes from this graph. So the same thing that I already discussed about it, that the pressure drop in the reaction turbine. So you have to go through it by yourself. So there is nothing difficult about it. Okay, so now we will just take a side-by-side comparison of impulse and reaction turbine so that you will get some idea. So in case of impulse turbine, the steam completely expanded in the nozzle and its pressure remained constant during its flow through the blade passages. In the case of reaction turbine, the steam expands partially in the nozzle and further expansion takes place in the rotor blade. Okay, so this we already discussed from the help of graph as well. The relative velocity of steam passing over the blade remain constant in the absence of friction. The relative velocity of steam passing over the blade increases as the steam expands while passing over the blade. So this is the reaction turbine. And then blades are symmetrical in impulse turbine, blades are not symmetrical in reaction turbine. The pressure on both ends of the moving blade is same. The pressure on both ends of the moving blade is different in case of reaction turbine. The steam velocity is very high and therefore the speed of turbine is high. In case of impulse turbine, the steam velocity is not very high and therefore the speed of turbine is low in case of reaction turbine. So this is just a basic difference between reaction and impulse turbine. So, okay, I think we already discussed this type of merits and demerits previously in the gas power cycle lecture. So the advantages of steam turbine, you already know that ability to utilize high pressure and high temperature steam, high component efficiency, high rotational speed, high capacity weight ratio, smooth, nearly vibration-free operation, no internal lubrication, oil-free exhaust steam, can be built in small or very large unit up to 1200 megawatt. Disadvantages for slow speed application, reduction gear are required. The steam turbine cannot be made reversible. The efficiency of small simple steam turbine is low. This is just an overlook of disadvantages and advantages of steam turbine. And then the application is in use in power generation, refinery, petrochemical, pharmaceutical, food processing, petroleum, gas processing, pulp and paper mills, and waste to energy conversion. Okay, so now important point over there is, because we are just looking for this whole rotodynamic machine lecture, because we are going to understand velocity diagram, because this is the main important point, that how to build the velocity diagram of the at the blade inlet and blade outlet, because this velocity diagram you have to use as a reference to find different parameters. Okay, so for example, this is a velocity diagram which is shown over there for our blade section, and that is the moving blade of the impulse turbine. So first I will draw this whole figure for you again, so that you will get some understanding. Okay, so for example, if we can just take a example that there is a blade that is the cup shape, and it is a impulse turbine blade, and it is moving with some velocity, and we call this velocity as u. Okay, so, and I already told you that, for example, if the steam is coming from the nozzle, okay, so this is our inlet, and this is the outlet. So now we assume that from the nozzle, the steam is coming out with some velocity, that is the absolute velocity, and this velocity is V1. Okay, so now here we have another component. So this component is same as the velocity u, because if the blade is moving with some velocity, so this component you can call as u. Okay, so this u and u is same. Okay, so now we have one relative velocity at the inlet. So we call as a, so one basically represent all the parameters that is at inlet. So here we can say that there is a relative velocity, and we call as a VR1. Okay, so now for the absolute velocity we have two components. One is tangential component and one is axial component. Okay, so we have to draw the two components for V1. So for example, I can say that this whole is the tangential component. So VW1. Okay, so VW1 basically world velocity. So world velocity is the tangential component of your absolute velocity. And now we have another component which is the axial component. So axial component is something like this. Okay, and we call it as a VA1. Okay, so this is the axial component of your absolute velocity. Okay, so between V1 absolute velocity and your blade velocity, we have angle that we call as a alpha 1. Okay. So this angle is alpha 1, which we call as a nozzle inlet. And then between VR1 and the world velocity component, which is this one, there is another angle which we call as a beta 1, and this is called blade angle. So beta 1 is blade angle and alpha 1 is nozzle inlet angle. So this is the velocity diagram at the inlet. Okay, another important point over there is whenever you have to calculate the tangential force, okay, that is acting on your blade, so you have to consider the world velocity component of your velocity, so which is the tangential component of your velocity. And if you have to calculate the axial force, then you have to consider for the VA1 or same VA1 at the inlet and VA2 at the outlet. And in case of flow rate measurement, the axial velocity component are used. And in case of your tangential force measurement, the world velocity components are used. So now we will go back to the outlet now, because inlet velocity diagram looks like this. Now if we consider that there is no friction on this area,
सर
G,
सर अल्फा और बीटा दोबारा बताइएगा.
okay, alpha, okay, so this is the absolute velocity, this is the blade velocity. So angle between absolute velocity, so absolute velocity is the velocity of the steam coming out of the nozzle. U is the blade velocity, and the angle between V1 and U is alpha 1, and alpha 1 is nozzle inlet angle. Okay, and then there is a relative velocity Vr1, and there is the world velocity Vw1. Okay, so the angle between these components, which is over there, is called beta 1, which is the blade inlet angle. Okay. So most of the time, the parameters, if you are going to solve the questions, so you have to calculate either these all alpha, beta, V1, Va1 by using the proper vector diagram or by using the proper scale. Or sometimes it is given in the question that this is your blade inlet angle, this is your nozzle inlet angle, so you just have to use these parameters directly. Okay.
Okay, sir.
So now we assume that on this area, which is the circular portion of your blade, or you can say that the concave surface, so there is no friction. Okay, if we consider that there is a friction, then we have to take. Okay, so it's vanishes over there, no problem. Okay, make. Okay, so if there is no friction over there, so we can take that the same velocity, that is the relative velocity Vr1 at the inlet. So now we have the relative velocity at the outlet also. So this is your outlet. I'm not going to draw inlet again. Okay, so you just have to correlate if you are drawing already. So here we have one component, and we call as a Vr2. Okay, so same Vr1 is at the inlet and Vr2 at the outlet. Okay, so now we have the absolute velocity at the outlet as well. So we can draw another vector to represent the absolute velocity at outlet. So we can call as a V2. Similarly, V2 is the absolute velocity, and this absolute velocity also has two components. One is the tangential component and one is axial component. So axial component, you can just draw one like this, that this is VA1, and then we have the tangential component. You can draw another line. So this is your tangential component, and you can call as VW. Sorry, this is VA2 and VW2. So world velocity at outlet, axial velocity at outlet, and absolute velocity at outlet. Okay, so now the same velocity which we considered, because U, so we have just represent the velocity which is in this direction, and it is also U. Okay, so now if we can take a look for the angles, so between U and VR2 we have, so in case of inlet diagram we have beta 1, so in case of your outlet we have beta 2, and then here between VW2 and V2 we have alpha 2. Okay, so alpha 2, and this all parameter we will discuss that what are the meaning of these parameters. So alpha 2 is basically angle made by absolute velocity V2 with the tangent of the wheel at outlet. So this is not just like that in the case of alpha, in the case of inlet we have alpha 1, which is the nozzle inlet angle, because here there is no nozzle, so that is not a nozzle inlet angle, and beta 2 is basically blade outlet angle. So this is the velocity diagram at the outlet. Okay, the same velocity diagram which I have already shown in the slide as well. So if you can have to draw, you just have to take this figure as a reference. So in this case, so only difference is I have drawn the blade like this and nozzle is over there. Okay, and in this case nozzle is at the upper side and then the blade direction is different. And rest of all the parameters are same. So V1 is the absolute velocity of steam at inlet, alpha 1 nozzle inlet angle, U blade velocity, and this is also U. VW1 tangential velocity of steam at inlet, VA1 axial velocity of steam at inlet, beta 1 blade inlet angle, beta 2 blade outlet angle, VR2 relative velocity of steam at outlet, VW2 tangential velocity of steam at outlet, VA2 axial velocity of steam at outlet, K blade velocity coefficient. So this blade velocity coefficient basically is only used if we are considering there is a friction. If we are considering there is no friction, okay, and most of the cases for analysis purpose, we consider that there is no friction over here. So we do not need to consider this K. So we do absolute velocity of steam at outlet, alpha 2 angle made by absolute velocity V2 with the tangent of wheel at outlet. So these are all the parameters which is come from velocity diagram of the moving blade for an impulse rotor. Yes, and I will suggest you have to draw these velocity diagram by yourself at the inlet and at the outlet by yourself so that you will get some understanding of it. So if you have any question, you can ask me, or otherwise we will take some break and then we will continue from this. Okay, so we will take a break of 10 minutes and then we will continue from the velocity diagram again. So starting again from the velocity diagram. Okay, so now here another important uh, you can say diagram, which is the combined velocity diagram. And this velocity diagram also come from the same velocity diagrams that we already draw. Okay, so if you can look over there. So what we have to do in the combined velocity diagram. Okay, so first important point is why we are going to make the combined velocity diagram, because it is more easy to analyze all these vectors, that is v1 or all these parameters listed in this slide, by if we have a diagram which represent both the inlet and velocity diagram at the same time. Okay, that's why we are going to combine the outlet velocity diagram and inlet velocity diagram, and we have to build one velocity diagram out of it, which is called combined velocity diagram. And the same velocity diagram which is shown over there will basically come from the combination of these two diagrams. Okay, so now we will try to draw this, and then we will see how to develop the combined velocity. Okay, another important point is that regarding to your marks that is uploaded in Moodle, so you have to look into it if you have any problem or issue that your marks are less, or you think that it will be more. Okay, so you have to just inbox me on MS Team before 29. After 29, I will not consider any request because I have to finalize the marks. So, and if any student whose marks are not there and he submitted to me any assignment, so still he can contact me before 29. Okay, so I will just quickly draw the inlet velocity diagram. So this is V1 from the inlet velocity, absolute velocity. This is U, and then we have the relative velocity. So relative velocity comes between, and that is VR1, and then we have the axial component. So you can just mark on the axial component over there. So VA1, and this whole is VW1, and this is EU, and this angle is beta 1, and this angle is alpha 1. So this comes from inlet velocity diagram, and now I will draw the outlet velocity diagram. So if we have U over there, and we have this is VR2, which comes from the outlet velocity, relative velocity, and then we have here U, and this is your absolute velocity. And absolute velocity has two components. One is the axial, so this is VA2, and one is the tangential, which is VW2. Okay, and again the angles. This is alpha 2, and this is beta. Okay, so this is the outlet velocity diagram. So now we are going to invert both of these. Okay, and I think we can only invert this one, and this one remains same, and we can draw the combined velocity diagram. And if you can notice over there, this U, which is the blade velocity, and here we also have the U, which is the blade velocity. So these two velocities are common. Okay, so we can draw on the combined velocity diagram these two velocity as a common velocity. So for example, if I can just draw, this is the U. Okay, so here I can see this is the U. Okay, so here from the U we have one V1, which is, so I'm going to draw the inlet first. Okay, so inlet velocity diagram. And by using this, I am going to invert all these figures. So this is now V1. So if you can notice, so in this figure, we have clearly shown that V1, we have U, okay, and the angle between these two are alpha 1. Okay, So now we have the relative velocity also, and which is at the started at the end of u. So you can just mark VR1. Okay, so same VR1 which come from inlet velocity diagram. So VR1, and now we have two components. One is the initial component, and one is the axial component. So this is BA1, and now we can say that this whole is VW1, and the angle between VR1 and this line is beta. So this is your inlet velocity. So now taking the U common, I will draw the outlet diagram on the same figure. So if this is U, so from U I can draw VR2. So I can draw this line as VR2 and make this vector as like this. And angle between U and VR2 is beta 2. So beta 2 come from the outlet velocity. Okay, so from at the end of the U, we have absolute velocity. So which we can draw like this, which is V2 at the outlet. Okay, and this V2 also have two components. One is the axial component, so I can draw one component like this. So this is VA2, and one component like this, which is VW2, and the angle between these two are alpha 2. Okay, and rest of the angle you have D. Okay, so this is how your combined velocity diagram look like. Okay, so just we have combined the inlet and outlet velocity diagram. So either you have to just take the reference like this one, or because if you can, first we have to draw it, and then we will see next one. If you have any question, you can also ask. Okay, so if you can look into this figure, so do not get confused that the angles are interchanged in this figure. The reason is because in the reference book, in this side, the author built the outlet, and in this side, they draw the inlet. So I have drawn inlet on this side and outlet on this side. Okay, so that's why the figures looks changed. So do not get confused. So either you can take a reference this figure, or either you can take the reference which I have. Okay, so now we have to look into some formulas which we can use in order to solve the numericals which are related to the velocity diagrams. Okay, so in all the numericals, most of the time, this velocity diagram is mentioned. Okay, and in this velocity diagram, either your absolute velocity is given, the angles are given, okay, and then absolute velocity at the outlet is given, and you have to find different parameters related to these. Okay, so first equation, for example, if we have to find the tangential force. Okay, so tangential force, I already told you that in order to calculate tangential force, we have to use the tangential velocity components. So that is mass flow rate into delta V. Delta V is change in velocity. So mass flow rate and mass flow rate basically is the steam output. VW1 is the work component minus VW2. Okay, so okay, from this figure, if you can notice over there that your world component at the outlet, this is the outlet, direction is on at your right side, and if you can notice from inlet, the direction of the world component is at the opposite side. So it's mean this is minus, you can say minus W2. Okay, and from this you can easily find out. Also, if you can just consider the case where we have draw. Okay, so the figure which I have drawn, so if you can look into it, you can easily find out that the world component is in the opposite direction. So that's why we, for the first formula, we have to use tangential force is equal to mass flow rate into world velocity at 1 minus VW2. So our relation becomes m dot VW1 plus VW2. So in this case, if we have the mass flow rate, tangential velocity at inlet, tangential velocity at outlet, so we can easily find the tangential force. Okay, and this force is basically responsible for the movement of the plate. Then B, which is the axial component. So axial component, which is equal to mass flow rate into VA1 minus VA2. So if you can notice over there, both of this VA1 is in the same direction, so we cannot change the sign for this. So if we have the axial component at the inlet, axial component of the velocity at outlet, and mass flow rate, we can easily find the axial force. Now formula C, which is the work done by the steam on plate. So I can say work done so it is equal to mass flow rate into VW1 plus VW2 into U, which is the blade velocity. Okay, so from this formula, we have the blade velocity and world velocity at the outlet, world velocity at the inlet, mass flow rate, we can easily find. And this unit is in Newton meter per second. So if you can notice over there, Newton meter per second, it's done out in watt. So similarly, if we want to find the power dweller, so power dweller formula. So it is equal to work done divided by 1000. Okay, so basically this work done by steam on the plate divided by 1000, it's converted into kilowatt. Okay, so we can use same formula, which is m VW1 plus VW2 into U, and find out the work done and divide by 1000, so we can get the in kilowatt. So that is the power developed by the turbine. Now the next formula, which is the blade efficiency. So in some cases we have to find the blade efficiency, and this formula is that work done, so same work done on the blade from this formula divided by energy supplied to the blade. This spelling you have to look into it. Okay, so work done come from this formula where we get the energy supplied to the plate. Basically, energy supplied to the plate come from, so energy supplied half m v1 square. So this v1 is basically absolute velocity of the steam that is coming out of the nozzle, and m is the mass flow rate because this is in kilowatt. Okay, so you have to just convert these units, or you can say it is in watt. Okay, because this is the mass flow rate. Okay, so if we have the mass flow rate and absolute velocity at inlet, we can easily find the energy supply. And if we get the energy supply, we just simply put into this formula, and we can find the blade energy easily. Okay, you have to note it down, then we'll move to the next slide.
सर एनर्जी सप्लाई वाला नजर नहीं आ रहा, वो उसको जरा
मैं भी दोबारा इसको लिख देता हूँ। So blade efficiency formula, we just have to further simplify it. So blade efficiency, so I will just write B. So it is M VW1 plus VW2 into blade velocity divided by half M V1 square. Okay, so this is the work done. The upper part is the numerator and denominator. We have the energy supply to the blade per second. Okay, so the mass flow rate we can easily eliminate from this one, and the simplified version of this equation is 2U VW1 plus VW2 divided by V1 scale. So if we have the tangential velocity component at inlet, at outlet, blade velocity, and absolute velocity, that is the V1 at the inlet outlet of the nozzle, so we can easily find the blade efficiency by using this relation. Okay, so now the next relation, which is the stage efficiency. The stage efficiency, as you already know, what is the meaning of stage? Stage is basically a combination of your moving blade and uh, that is the stationary blade. Okay, so for this, the formula is that the same work done on the blade per second divided by previous case we have energy supplied to the blade per second. Now we have total energy supplied per stage. Okay, so this WD, which is the same formula, so mass flow rate VW1 plus VW2 into blade velocity, and now the total energy per stage. So this, because there is an involvement of total energy, so definitely we have to look into the enthalpy value. So for here you can see that so there is a heat drop, so M H1 minus H2. Okay, so this we will look into it if we need it, and the problem statement that how to find these values. Okay, so till now you just have to note down these formula because we have to use these formula while solving the problems related to the velocity diagrams. So these all formulas are written over there as well. Okay, so you have to go through it by yourself. Okay, I will pass the slides to you. These all formulas are mentioned in the slides. Okay, so we will stop at this point, and from the next class we will try to solve some problem. But we can start here, so we could not finish within time. Okay, so if you have any question, you can ask me. Otherwise, we will just stop.